So we've talked about 3 trends so far, so now we're going to take a look at how we can use these trends to examine relationships between our elements. We're going to look at rubidium, sodium, and beryllium, strontium, selenium, and neon, and iron, phosphorus, and oxygen. I'm putting up this periodic table so you have it as a reference. You may want to get yours out. The big thing to think about with size is that as you're moving down and to the left, you're going to see your sizes of your atoms get larger. Francium is our largest atom, whereas helium would be our smallest. So when I'm trying to rank these in increasing size from smallest to biggest, I'm going to find rubidium, I'm going to find sodium, and I'm going to find beryllium. And I want to find the one that is furthest away from francium, because that one's going to be my smallest. So that would be Be. The one that's closest to francium is going to be my largest. That would be Rb, and Na would fall in between. So Be, then Na, then Rb. I'll do the same for strontium, selenium, and neon. Sr, Se, and Ne. Again, the one that's the smallest is furthest away from francium, which would be neon. The one that's the largest is the one that's closest to francium, strontium, and selenium will fall in between. Finally, I have iron, phosphorus, and oxygen. Same rules apply. Oxygen's furthest away, then phosphorus, then iron. And so iron will be my biggest and oxygen will be my smallest. You may want to pause here if you've not had a chance to write that down, or if you want to take any notes about what we were just talking about. Next, we're going to look at ionization energy, and we're focusing on the first one. So we've got our 3 sets again. Remember, with ionization energy, we're going to have larger ionization energies as we move across. So helium is going to have our largest ionization energy. Francium is going to have our smallest. So if I look at the order, if I want to go from smallest to biggest, the smallest one this time is going to be the one closest to francium, and that would be Rb. The one with the largest is going to be the one closest to helium, which will be Be, and sodium will fall in between. So these actually were already written in order from smallest to largest ionization energy. Strontium, selenium, and neon are my next choices. There's strontium, there's selenium, and there's neon. Again, our smallest is the one that's closest to francium, because it's going to require the least energy to give up an electron. So strontium will have the lowest, neon will have the greatest, being the furthest away, and selenium will fall in between. Finally, we have iron, phosphorus, and oxygen. Again, smallest is the one that's closest to francium, largest is the one closest to helium, and then again, phosphorus will fall in between. I promise this is not the way they always turn out. If you haven't had a chance to write all this down, I would pause this before we move on to the next slide. Our next question asks us to order the atoms in each of the following sets from the least exothermic electron affinity, so the one with the smallest electron affinity, to the one with the most. We have N, O, and F, Al, Si, and P. Now remember again, francium will have one of the smallest electron affinities, whereas helium will have one of the greatest if it was going to gain it. So I want to find which one is going to have the smallest by the one that's furthest away from helium, which would be nitrogen, and the one that will have the largest is going to be the one closest to helium, which would be fluorine. If I look at aluminum, silicon, and phosphorus, the same policy would apply. Phosphorus is the closest to helium, so it would have the largest. Aluminum is the furthest away, so it would have the smallest. If you haven't gotten this down, you might want to pause it before we move on to the next slide. Here we're given the electron affinities for the elements from aluminum to chlorine. So there's aluminum, there's phosphorus, there's sulfur, there's chlorine, I think. Sorry guys, it's been a little while since I've seen these. But if you look at your periodic table, you'll be able to tell these. And so it says that we're increasing. We're seeing a jump here from negative 44 to negative 120. And then we're seeing another jump from negative 74 to negative 200.4. And we're seeing a final jump of negative 384.7. So our largest electron affinity is seen with chlorine. And so that kind of makes sense. If chlorine gains an electron, it becomes like the noble gas that comes after it. And that would make it really, really stable. This one here would be one away, so it's going to have a fairly large electron affinity. It's getting closer to having that noble gas configuration. Phosphorus here, if it gains one more electron, it will have a half-filled p sublevel, and that's why we see a little bit of a jump from our first aluminum, which would go from having 1 p electron to 2, to phosphorus, which would go from having 2 p electrons to 3. This says all follow the expected pattern for electron affinity except for phosphorus. Again, you can write down what you would like for this. And the reason we see an increase for phosphorus, a spike there in the middle, is because of that semi-stable configuration that will be that phosphorus will acquire as a result of having a half-filled p sublevel. Alright, this question asks us to take a look at the electron affinity values for the elements between aluminum and chlorine on your periodic table. So aluminum would have an electron affinity of negative 44 kilojoules per mole, silicon of negative 120 kilojoules per mole, phosphorus negative 74 kilojoules per mole, sulfur negative 200.4 kilojoules per mole, and chlorine negative 384.7 kilojoules per mole. So we see that the electron affinity values are becoming even more exothermic, with the exception of phosphorus. We see that phosphorus's electron affinity value diminishes slightly, and then we go back up for sulfur and chlorine. Why this is happening? When phosphorus gains that electron, phosphorus already has a half-filled set of orbitals in that 3p sublevel. We see that phosphorus goes from having the noble gas equivalent of neon, 2s22p3, and when it gains that electron as part of the affinity, it goes from being that half-filled sublevel to having a second electron in one of its 3 orbitals. Remember that electrons have the same charge, and therefore they repel each other. And by adding on that 4th electron, the repulsions that are taking place in those orbitals are going to increase. As a result, phosphorus is not as inclined to gain just 1 electron because only one of its 3 orbitals are dealing with that increased repulsion factor. So that's why you see a little bit of a dip in its electron affinity. It will gain an electron, but it would prefer not to just gain 1. You do not have to write all of this down. Write down what you would like. But the big thing to note with this one is just that this dip in the value is due to going from being in a half-filled, fairly stable electron configuration to a less stable electron configuration because the electrons are no longer in balance with one another for that energy level that contains 3 orbitals. The last part we're going to talk about today are isoelectronic ions. These are ions